Yep. Yes, we see it in full screen mode.
Okay, perfect. So thank you. So my name is Henri Boffin, and I work in the user support department of ISO. And I'm also the project scientist of the new ISO exposure time calculator. And I will give you then a brief introduction about what the ISO ETC is, and mostly showing you how to use it. But before I start, I would like to acknowledge my colleagues, Jakob, Lars, and David, who are the ones actually doing the work. I am only coming with the crazy ideas, and then they are the ones who have to try to implement it. So I also understand that we have here a very diverse group of participants to the workshop. So I will also try to go back to the fundamentals for the newcomers, those that never did observation and so. And so I hope that the more experienced observer will bear with me, and that at the end they will be rewarded by seeing a preview of the new ISO ETC. So as you heard this morning, if you have a great idea, you should definitely try to submit a proposal, and we assume that you have selected your instruments from all the suites available, but now you have to convince the time allocation committee or the OPC that they should give you time on the VLT or on the NTT and so on. But telescope time is a very precious thing. There is a huge competition, as we saw, with large overhead factors, and it's very expensive. So we should really only ask for the time that we need for the observations. If you ask for more time than what you can justify, your proposal will likely be rejected. But on the other hand, you don't want to ask for too little time, because you want, of course, to achieve your science goal. So the time that you will ask, or that you need to ask, in fact, will normally be decided by the signal-to-noise ratio that you need for your science. So here are just some basic examples in imaging or in spectroscopy, where I show images and spectra, where the signal-to-noise ratio is changing between 3, 10, and 100. And of course, you can see that you get much better data in both cases. And depending on what you want to do, you will have to select one of those signal-to-noise ratios. So if, for example, if you need very precise radial velocities, or if you want to determine the chemical abundance of an element, you may need to have a very high signal-to-noise ratio. On the other hand, if you only want to detect an emission line somewhere, then maybe a signal-to-noise rather low would be enough for you. So this is really the first thing that you have to decide is, what is the signal-to-noise ratio that I need to reach my scientific goal? And this is, of course, very important, because, as you know, the exposure time will basically be proportional to the square of the signal-to-noise ratio. So going from 3 to 100, you increase the exposure time by a factor 1000. In some case, it's not really the signal-to-noise ratio that you want, but something else. Like, for example, if you are doing polarimetry, it will be the precision which you can get the polarization fraction. If you do interferometry, it would be the visibilities or the closure phase that you want. And if you do adaptive optics, maybe what is most interesting for you is the Strela ratio or the contrast ratio that you can achieve. So I'm here talking about signal-to-noise really as a proxy for all of those. And I will continue, for simplicity, to only talk about signal-to-noise ratio. So that's where, of course, the exposure time calculator comes in. So what is an ETC? An ETC is basically the tool that will allow you for a given instrument and even a given instrument mode to predict you the exposure time in order to get the required quality or signal-to-noise ratio that you need for your science, depending on the various parameters. So this can be necessary for phase one, so the call for proposal, which is now. It can also be necessary when you will be planning your details of your observations. So when you are going to make your OBs, it's also used more generally at any time by the astronomical community before, during, or after observation. If you want to check, why don't I get the signal-to-noise ratio that I was hoping for, you can try to go back and see that. And ESO staff may also use it, or other, the consortia can use it to do instrument studies, to do development and commissioning, and so on. Oops, sorry. That's too fast. So, but what is very important to realize is that the ETC, at least in its present form, and not yet in the for the foreseeable future, does not include overheads. Okay, so this is something that you will have to compute yourself using the information that is linked from the call for proposal, and you have then to add these overheads into your request for time in P1. And I suppose Oli is going to discuss this just after me. So again, just to go a little bit more precise and go back to the fundamental and maybe also demystify a little bit what the ETC is doing. So here just the typical way that you compute the signal-to-noise ratio in the case of photometry. So basically what you are going to do is simply counting all the electrons that came on your detector per unit of time times the exposure time. Yeah. And so what you need, of course, is a radius that is large enough so that it will encompass most of your PSF, but it should not be too big, in fact, to reduce, so not to add too much noise to it. And so basically what really the ETC, and this is the main part of the ETC, is to know what is the value of the radius that you need to consider, or more precisely, what is the shape of the point spread function that you should put into your model. So if you are doing normal imaging, so and you are seeing limited, then we will generally use a simple Gaussian with the full width Al maximum, which is basically given by the seeing with an additional terms maybe coming from the telescope and so on. But in some case, we may use a Moffat profile, and for adaptive optics in observation, we will change the full width Al maximum that will go into the PSF. And in some case, we are even obliged, because it doesn't look anymore like a nice Gaussian or Moffat profile, we really have to use tabulated form of the PSF. And this is going to be the main ingredient into the ETC. So this is the signal that you get, but of course we have also noise sources. So we have, of course, the shot noise from the source, which is simply the square root of the signal. We will have the shot noise from the sky that is in your given aperture. And they are also sometimes coming from the detector. So we will have the readout noise, and we will have the church noise from the dark current as well. And those will be then added. So this means that the ETC needs also to have a very good model for the sky contribution so that it can compute the noise due to the sky in the signal-to-noise ratio. And it needs to know information about the detector. So it needs to know what is the readout noise, what is the gain, what is the dark current, and all of that. And then when you combine all of that, this is what you get. I guess most of you, or I'm sure everybody of you, is familiar with this formula. So this is the signal-to-noise ratio, which is the signal divided by the noise, which is then added, all the noise terms are added in quadrature. And they are simply, then we take the square root of them. So this is basically what is at the core of the ETC. And really the whole trick is to be able to know how to compute the various terms that enter this formula. So the ETC at ESO, they are all web-based. So you don't need to download anything onto your computer to run it. They're all on the web, and you have to fill in the information. So for most instruments, those are static web pages in which you will enter information, and then you will click on submit. And then you get a new page where you have the results like plots that will be provided, or ASCII files or fixed files. And then, for example, you can see what is always my CM2NOS varying with the wavelength range, with the seeing, with the exposure time, and so on. And based on that, you can then decide what is the most adapted CM2NOS you will want, what should be the best conditions you should request, and put them into your proposal. So at ESO, most of the webs, the ESO ETC, sorry, are available on this link here, but in the future they will be linked from this link here, which is much more easy to remember. For the moment, if you click on this one, you will only go to the newest ETC, but we will change that so that it goes to the full list of ETC. So let me now try to go and show you the this web page. So I hope you can see. Can you see still something, John?
No, we only see your PowerPoint window because you shared specifically the window rather than the entire desktop.
No, that's what I tried. I am sure I did not share the window. I shared the desktop, but okay.
You see the PowerPoint window.
Okay, so then let me stop sharing. Share. Okay, desktop. This one, then, I guess. So, do you see now the website?
Yes.
Okay.
Yes.
Sorry for that. So now you can see then so this is the main web page, so which will be linked to etc.eso.org soon, and then you can see then all the various instruments for imaging, spectroscopy, and all the ETCs. And there's also VLTI if you care about that, and you can also play with already have some idea about what the ELT will allow you to do. If you are curious about that, I want to know. So before we go to one specific instrument, let me also first show you above here that we have here what is called the Sky Model Calculator, so SkyCal. And so this is very useful because it allows you to really know what is put inside the ETC in terms of Sky model. So this is the Zero-Paranal Advanced Sky model. And you can select it for Lacia, Paranal, or even for the ELT sites. And then you can put information here. And you can see what are the different contributions to the Sky model that you can select. And what is useful is that you can also here choose, for example, the wavelength that you are interested in. And you can then get some plots. And so, oops. Okay, sorry. Yeah, I was too. So you can share some plots here, for example, and the good thing is that you can also download those files as ASCII files, which means that you can also then use them and compare them to your spectra and see, for example, whether a line is a telluric line or not, and compare the relative contribution. So this is also maybe useful to know and to use sometimes to really make sure is what I see in my spectrum, is it really from a star or is it coming from the sky? So I understand that many of you prefer Muse, so I will go then to the Muse ETC. So most of the ISO instruments for the moment are really following the same pattern. So we have here a static page where you will type in your information. So as you see, the first thing that you have to define is what is the target? How do I define my target? So you can choose if it is infinite, if it is extended, if it is a Celsius profile, or if it is a point source. So let's assume for the moment that it is a point source. And then you can also decide whether you want to get the signal to noise at the center or slightly offset with a limitation of 7.5 arc seconds. Of course, this only works if you have used an extended source, not for point source, because then if you go away from that, you are going to get no flux. And you would then get defined also what is the spectral energy distribution and the brightness of your target. So again, you have the choice among various things. You can define a uniform black body, which you give them temperature. You can choose a template and then choose a star, a nebula, galaxy, or quasar. So let's assume that we have an O9 star. You can then specify the redshift, and you specify also the magnitude. So let's assume it's magnitude 15 and it's redshift 1. So this then what you can also do, and this is not the case for every instrument, but it's the case for Muse and for some others, is that you can also now put a background source on top, below your real target. And this may be useful, for example, if you are looking at a supernova on top of a galaxy or something else. So here again, it will be the same thing. Your background, you will define it as being what kind of source it is and what SCD and brightness it is. So let's assume that my background is a Celsius profile, and I will take as a template that it is a galaxy, for example, which is of course also at redshift 1, and let's leave it like that. So once you have that, which I guess for the moment everything is very straightforward, you have to define your instrument setup. Okay, so here you can choose in Muse as basically 5 modes, and that's why you can choose among those modes. So either you use it in the wide field with no AO, you can use them in the nominal or extended range, wavelength range, or you use it with AO, again in the nominal or extended wavelength range, or you use it with the narrow field mode with AO. And you can then choose also how many pixels spatially you are going to go at, depending on your sense case, whether you need or not spatial resolution, or if you are interested in a bigger region. So you can really choose among a set of things available here. And the same way, you can decide to go at the number of pixels in the spectral direction, depending on, again, your science case, what you want to do. So this has now defined both the target, the background, the instrument setup. So what we are now working on is going to go to the sky conditions. And there you can use either the full almanac, or you can simply override that if you don't want to bother, and click here, and then you only need to specify what is the moon phase, so whether you want to have full moon or dark time, and the air mass, if you don't want to go into much more detail. But if you really want to have a full account of what you will get, then it's better to use the full almanac. So of course, This is using, no, this is, so the time that is there, it's day in parallel, so this is not going to be, of course, possible to observe yet, so you will change. But the first thing to do would be to introduce the target. So let's, for example, assume this one, and then we can search, and it's going to call Simbat, and then it retrieve automatically the coordinates of your target. So, of course, here I took a galaxy, but it is unfortunately in the north, so I will just cheat, and I will change the declination, assume there is an object there exactly symmetric, so now it is nicely located in the south, and it is well nicely visible in parallel. But of course we are in daytime, so let's go into the night by changing by 1 hour and click on the plus here. Then I can move, and you can see this is the time then of the observation, and this is when also the moon. So we can see, of course, for the moment there is a moon which is still, we are in bright time, of course, with moon which is at 0.8 Fi. So here we are very high. On the target is well visible at an air mass above 1.3, so I will assume this is fine. But let's now see what would happen if we are not going to observe in bright time, but in dark time. So then I will look what it looks like in 2 weeks from now. So I change 2 weeks. Okay, so now you can see, of course, my target is at the same position, but now we're in dark time. The moon has set, so this is what I want them to check. So you can really play with that, and then you can see what is the effect, what would be the various conditions, and compute the various CN2 ratio for those things. And then you can really use that to set your constraints on your air mass, on the moonlight, on the moon brightness, and so on, that you will then put into your proposal. So the other things that you have to put in your proposal will be the turbulence category. So Ollie will explain you that later, that this is, so basically which turbulence category, so which is a probability that those conditions are met in parallel, whether it is 10, 20, 30, 50, or 70, 85, or 100%. So here I was using the wide field mode without AO, and in that case you can see that the turbulence category is only, in fact, represented by the seeing. If I now say that I want to use the narrow field mode with AO, there I am using adaptive optics with the laser, and then you can see that in fact now the turbulence category is not only a question of seeing, but it's a combination between seeing and the turbulence, the time in the atmosphere, so the tau naught. And so if you want to have a 50% chance, the seeing must be better than 1 second, and the current time has to be larger than 3.2 milliseconds. If you want better conditions, you can of course select those. And you can also see that this mode cannot be used in all conditions, because if the seeing is too bad or the current time is too small, then you cannot use this mode because you will not be able to do any correction. So this is not offered here. So let's assume that this is what we want. And so we are almost there. So what we now need to specify is you can define the reference wavelengths, which is, for example, if you're interested in a given wavelength region or a given line, this is where you want to compute the signature ratio. This is where you put that value here. And you can also decide which wavelength range to plot. So this is the wavelengths automatically of the region that is covered in the nominal mode, if you would use the extended mode, it would change this value here. But you could also say that you are only interested in a much smaller range, and you could change that. And then you can decide what you do, either you give the signal-to-noise ratio and the number of exposures, and the ETC is going to tell you how much the exposure time should be. You can give the exposure time and the signal-to-noise ratio, or you can give the number of exposures and the exposure time, and you get then the signal-to-noise ratio. So in my case, I want to be able to detect my object with a signal-to-noise ratio of, let's say, 100. And I want to do 4 exposures with Muse because I want to do 4 rotations of 90 degrees, which is preferred for Muse in order to do the data reduction. Instead of doing only 1 exposure, you generally do several, which are rotated by 90 degrees. And so I will then use here 4 exposure time. Okay. And then after that, what you do is basically you select what kind of information you want to plot. You can select various plots, and you can also download some feeds file if you are interested to know how they look like. And then, as I said, we click on submit, and it will then give you the results. So here is first a summary. If you are interested, you can also see the details of the formula, how it did compute. So you see again our famous formula coming here, and that it gets then a signal-to-noise ratio at 100, so with the exposure time that it will give you. This is a summary of what you have given in. You can again show the model configuration details if you are interested in that. And finally, this is the result. And so in our case, what is the most interesting is that it tells me that I have to ask for 375 seconds per exposure in order to reach then my signal-to-noise ratio of 100 after 4 exposure, for a total exposure time of 1,500 seconds. Of course, again, very important, this does not include the overhead, so you will have to include that by hand yourself. So, you can also then see the plot. So you see here I put a reference wavelength of 550, and this is where indeed the signal-to-noise ratio is 100, but I can see how it changes as a function of wavelengths. So let me know. So this was for the ETC in the current configuration. Let me go back to the presentation. I hope you see the slide, John.
Yes.
Okay, perfect. Thank you. So this is indeed the current situation that we have. So we have, as you may know, or you will see in the next talk, we have the phase 1, we have the phase 2. They are both the ETC. They are all online. And phase 1 and phase 2 use really the similar look and feel, while DTC is a little bit, for the moment, independent. You have seen it here. It has a different look and feel to P1 and P2, and there is also no direct link to them. So as I have shown you, you will get the information about the exposure time that you will then put by hand into the phase 1, and it will also tell you which is the turbulence category that you have to type in by hand into the P1 and so on. So there is no connection. So this is not the ideal situation, of course, and ESO is working on improving this thing. So this is now the goal of what we call the ETC 2.0, which is a project that we have been starting at the ESO. And the idea is really to incorporate everything together, and also, as you have seen already a little bit, incorporated with Simbat, but maybe later as well to the archive and so on. And the idea is also to have a full similar look and feel. This is the basically concept for those that are, really want to know the behind the scenes things. So the whole idea is that there is a front end, which is the web browser for standalone etc. phase 1, phase 2. There will be the possibility to connect with command line. The archive and quality control hopefully will also be able then to connect to the backend, which will connect. Oops, I don't know why it doesn't. So it connects to the etc services and the etc calculation engine. So this is really what we hope to achieve for some instruments in a few months. Hopefully, 1 or 2 instruments will be fully integrated like that by the end of this year. And so for the most techno-savvy among you, this is the technology that are used for this ETC 2.0. So the front end is similar to P1 and P2. So the idea is to use the Angular framework, and it's really a one-page web application framework. So you don't quit anymore your page to go to the result page. It's all done on the same page. It's used in P1, P2, the same thing, and it follows the same standards. And the backend is being completely rewritten to have a very concise Python code and really using the scientific computing standards, which is NumPy, SciPy, and AstroPy. And the connection with the front end is done by a Django web framework in Python. So this is how it looks like. I'm not going to spend much time because I'm going to show you a live demo now. But you can see everything is on one single page. So both what you type in and the results are all in the same page. What is important is that it is all using JSON files as both input and output. And you can use the input JSON file also on a command line or with a script. So to call an API so that you don't need necessarily to use a web interface. And the output is also available as JSON files, so you can also read them in Python. So let me then try to go back to the demo. So this is how it looks like. I hope you see it well. Yes. So this is the Cryos ETC, which will be available next week. And again, you can see that we have now the same things as for the ETC1, but they are now put into tabs. So we have again the target definition, the sky, the thing, the instrument mode, what you want to do, and how to select your plots. So for all the other instruments, you will need to use still the old ETCs, and we are going to hope to migrate them to this version in the next 1 or 2 years. But if you want to apply for the Cryos time, then this is what you will need to use. You will need to use the new ETC for Cryos. So there again, you will define for the target, the morphology. For the SCD, you can choose a spectrum, you can use a template. There for the moment, you choose if you want pickles, marks, models, or quasars. This is unfortunately the only models that we have now that span the full wavelength range of Cryos in the near infrared, but we are working in trying to update this. And then if you want marks model, then you can select among the various models. For the moment, it's very not very user-friendly long list that you have to select from, but we are working on improving that as well. So you can also choose a black body or Polo, or you can also upload your own spectrum if you prefer. So, and for that you can either upload it as an ASCII or a FITS file. So if you want, for example, to apply it to have simply an ASCII file, this would be the format. So you simply put two columns, one with the wavelengths in the meter, and the other is the flux density in, for example, hertz per second per square centimeter per angstrom or so on. And you can also put comments which are ignored if they are with the DS in the front. So if you so you can then simply upload this into the selecting your file and upload it if you want. But let's be simple for the moment. So, and what you can also do is you can apply a radial velocity or a redshift to your data. So, for example, if I want to apply a radial velocity, then I could put it in. It might be that I don't know it like that, so you can then try to look it up and either you type in by hand your coordinates and the date when you want to do the observations, or you can again use Simbat to do that. So for example, you type here your name of your target, and Simbat is going to resolve it, and you can then. So let me, for example, try to look for Aldebaran, so you can see that it found it, type in the propositions of the target, and I can then say compute and assign, and it will automatically fill in the field here for radial velocity and for the bias centric velocity corresponding to the date that I put here. So this is an easy way to also add your radial velocities. And then you, of course, define what is the brightness of your source and the magnitude. So for the sky, here it is much more simplified. So you only, for the moment, can choose between the air mass and the FLI that you want, as well as the vapor, which is more critical for cryo, of course. So you can choose which, if you want very dry conditions, or if you don't care about them. And so. Then again, you will have to define what, if you want to use an AO or non-AO mode. So if you use the no AO mode, the turbulence category is again only proportional to the seeing, and it tells you what is the turbulence category. This is what you will have to fill in P1, while the IQ that you will have to use, this is what you will need to fill in your OBs in P2. If you are using AO, there again you choose the turbulence category, but you have also to specify what is the magnitude of the NGS star, the airband magnitude, because this is also something that you need to do, and you need also to fill that in P1. So you need to provide this magnitude both in P1 and in the ETC, and as well as the spectral type. You can also then define what is the extraction aperture. So there is a default, and it tells you here what is the size that it corresponds to. So you can go, so this is 27 pixels corresponding to this size, but you can choose and say, well, in fact, I know my object is going to be bigger, or I want really only the central regions and so on. So you can change this amount. And then again, you can change the settings. So here you will change what is the setting that you have chosen, if you are in Y, J, H, K, L, M, and bands, and which various setting that you have here, and which order that you need to select. You select the slit width and the polarimetry. But for the next call, polarimetry mode is not going to be offered yet, so that's why those are gray out for the moment. You cannot yet select polarimetry. And then again, you can decide what is your date, what is going to be your end date, and you put it here, or you can select, oops, that's because you do. So this is a test version. So there is no guarantee that it works. It worked yesterday. Well, it works fine. And no, this doesn't work for the moment. So, but it will work next week, promise. So it's just that we are still working in the beginning for the moment. And then finally, what you do is that you select the plots that you wanted to show. So you can choose many different plots. For example, you can say that you want to see what is the sky looking, what is my target. You show them again. And so you see now that I have three kind of plots. So as I mentioned, you can, in fact, also, this is all based on input files which are in the JSON format, which is this format here. So you can always see what is in fact sent from the front end to the back end in the JSON format. And you can then either copy it to the clipboard, or you can download it as a JSON file. So if you download it, then you will be able to use it also in order to do a call on the command line. And I will show you how to do that. And similarly, here, all the data that are here, you can also download them. So all the plots that you have asked to do, so if you have here 3 plots that you have asked, you can then download them and then say that this is what you want to download. And you could then use scripts to look at them. So let me finish by showing you that. So so one way to do it, I mean, don't bother about trying to note all of that. I mean, this will be, well, first you will be able to see that in the video, but also it will be put on a web page where we will explain clearly how to do that. But you can use a script that we will make available that allows you then to use the etc on the command line interface. In this case, we want to use Claris, which is with foremost are the only 2 instruments where we can use the etc 2.0. This is the input form that you can that you want to send to the backend, which is the one that I downloaded. But of course, the idea is that you would download it and then you would change in your favorite editor. You will change some of the parameters, try to see how they look like, and then you will run it again, but you don't want to do that necessarily all the time on the web. So you may want to then do that with a script, and you will change those things. And then you mention simply what is the output file that you have. And if you run that, then this is now calling the API, and it got the files. So what it got is this etc output, which is again a JSON file, which is not, of course, easy to read, but you can use then another script that we will also provide, which is a JSON to ASCII Python script that will transform this output file into a set of ASCII file for the various orders and the various detectors of queries. So you can then, those are simple ASCII files that you can then simply, so you see this is just wavelengths and whatever the SNR that you obtain in that case, and you can then use that to put into your own script to visualize and so on. As you have seen, I also downloaded the output itself from the web. And so if I wanted to use these plots, because of course now those plots are there, they are very nice, but they're on the web. If I want to use that and I want to put that in a publication also, or in another Python script, then you can also use another script. It will be made available, which is called etc plot reader. And this is reading this output file. By default, it will read the one that is downloaded with the correct name, and it will create some plots, as you can see. So Python plots, the ones that were normally the same, while in this case I use a different output file, but it recreates the plots. So you can choose which one, and also it has written down in ASCII format all the data from those plots, so you can also reuse them. And finally, you don't need necessarily to use a script to query the API of the ETC. In fact, this is just, you can do that just with a wget command. So it's just with a post method. And again, this is the JSON file with the information that you want to send. This is the URL of the API of KS2, and this is then the output that you get. And this will do exactly the same thing, and it will also download the JSON file. And I think I will stop here. I may be just on time, and thank you very much.
Thank you, Henri. Excellent. Indeed, just on time, or just a teeny tad over. There was one question, but it's rather technical. It's just maybe you do know. Why was JSON chosen as the input-output format rather than FITS, for example?
Because JSON is indeed the standard which is used in the Django framework and the Angular framework. I mean, this is really apparently the standard that is nowadays used to transfer information much more than FITS. FITS is, of course, used in astronomy. JSON is used by the whole world of. So I wouldn't, I mean, this is indeed a very technical question that we should ask to our developers. But I think the main reason is because this is really the standard for these kind of things.
And I think given the amount of information that you need to feed in, FITS would be an overkill, for at least for the input. For outputting spectra and so on, maybe FITS could be useful, but indeed, in most cases, I think it's an overkill. And it's certainly more user-friendly to have it in JSON format for exposure times and simple lists and information like that. Okay, no other questions. So thank you again, Henri. And we'll move on to Olivier Aino.